Hello. In this lesson, we look at something called quartiles, the interquartile range, and then box and whisker plots are all tied in together. What it is, it's a graphical way of displaying data, so it's still looking at descriptive statistics, whereas in the last data set that we looked at uh, the empirical rule through the normal distribution. Today we're going to look at what applications can be had from a box and whisker plot or a box plot, or synonyms. So here's an example of two box plots just to see kind of what you naturally might think when looking at it, what you know, what's your background knowledge. So maybe take a minute, pause the video. If you look at the two box plots shown, this is comparing average gas prices between eastern and western states. Maybe write down 3 things that you notice, and I'll come back and share some of the things that I noticed, then we'll move forward looking into how we construct our own. So pause the video now. Okay, welcome back. The first thing I would say maybe is, well, this red bar in the middle is actually going to be the median. So it looks like, you know, the typical gas price in the west looks to be higher than the typical gas price in the east. It's more to the right. Maybe another thing you might notice is that the eastern states are more closely grouped together. Their range is definitely smaller. And it almost looks symmetric too, whereas the western states, it looks like there's some type of skewness going on here to the right. There's a larger tail going on to the right. The distance between the median and this far right is much smaller than the distance between the far left value, the minimum, and the middle value here. So those are just some things you might notice in looking at a box plot. If you didn't notice them right now, then maybe you'll notice them after the lesson. So first thing we'll do is maybe construct our own. The situation to start says a politician is preparing a speech and is going to discuss nuclear power. As his fact-check researcher, you find the number of nuclear power plants in the top 15 nuclear power producing countries in the world. And here's the data. So like the smallest of the 15 only has 6 nuclear power plants, and then the largest has 104 nuclear power plants within their country. You organize the data, and when you do so, it might be important to know where the middle is, and we call that the mean, and then we have a lower half and the upper half. And the first thing we're going to do is calculate what's known as the 5-number summary. The 5-number summary is a list of data values that occur when you list your data from lowest to smallest. It's the following 5 values of a data set. And note, we and the calculator, we exclude the median when finding the upper and the lower quartiles. So the first value that could state would probably be the median, I would imagine. Most people are going to, stay where the middle is. So the median is the middle value in the data set, in this case 18. Then what we find are probably the minimum and the maximum. So the minimum is the smallest, 6 here, and the maximum is the largest, 104. So far we've got the middle, and then we've got the extremes, the smallest and the largest. The other 2 values we can find are going to be the middle of the lower half and the middle of the upper half. And we call that the lower quartile and the upper quartile, because what we're really doing is we're splitting our data set into 4 pieces. The lower quartile, so the lower half, if I look at this, I need to find where's the middle of these. And the middle of these are going to be at 10 because there's 1, 2, 3 above and 1, 2, 3 below 10 in the lower half. So the lower quartile, Q1, would be the middle number between the minimum and the median, not counting the median in your lower half, and that's going to be 10. The upper quartile, that is going to be 31 because there are 1, 2, 3 values above 31 and 1, 2, 3 values below 31 in the upper half. So the upper quartile is 31. So what we've done is we've kind of chunked our data set into quarters, between the minimum and the lower quartile and the median. You'll also hear the median. You could refer to it as quartile 2 because quartile 1 is the lower quartile and quartile 3 is the upper quartile. And then median to upper quartile and then upper quartile to maximum. So 4 pieces. That's why we call them quartiles. You can also use a graphing calculator to find the mean and the standard deviation and the 5-number summary that we've done before. So we did this in the prior discussion. We used the graphing calculator to find the mean and the standard deviation. You can also use it to find the 5-number summary. So if you go to stat, I'll show the steps. I'm not going to actually type in the data just for sake of time, but you can do it yourself and check. You go to stat, you go to edit and enter your data. So if you have data in there, you might want to clear it out of L1, and you don't necessarily need to do it out of L2 because it'll just use L1, but it might be a good idea. You enter your data set into L1, so all of our numbers for our nuclear power plant. And then you're going to go to stat, Again, once you've entered your data, over to calculate, you're going to choose one variable statistics. We only have one variable, and that's number of nuclear power plants. You hit enter, and it will output the following data. You might need to scroll down when you output it, and at the bottom, it actually will output for you the 5-number summary, and here it is. The minimum is 6, quartile 1 is 10, there's our median of 18, there's quartile 3 of 31, there's a maximum of 104. So it outputs for us the 5-number summary. It gives us a good idea of what data values and how our data is spread out. I'm going to ask you to try it. So, the following are the prices of 10 houses in the Helena area in thousands, is shown below. So, it varies between $135,000 to $700,000. I'd like you to state the 5-number summary of the data above. And also note, if there is no middle value, the average of the average of the two in the middle acts as the middle value. So, pause the video now, come back once you've had a chance to try it, and see how you did at finding the 5-number summary for this data set. Okay, welcome back. Just a quick spot check on it. The minimum is 135. The maximum is 700. The median, well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 data values in our data set. And we talked about this when we were calculating the median before. If there's an even number, then you're going to have to average the two middles. And the average of the two middles is going to be 240. So the median is 240, the minimum is 135, and the maximum is 700. Now I have to find the middle of the lower and the middle of the upper. So my lower portion are these values, and the lower of that is going to, or the middle of that is 180, and the middle of the upper portion is 300. So there's all 5 of the values you should have found for the 5-number summary. Once you have the 5-number summary, you can then use it to construct a box plot. And a box plot is a very helpful descriptive statistic. It's a chart, graph of sorts, that allows me to see how my data set is spread out. So box plot is a visual way to display the distribution of a data set based on the 5-number summary. It's particularly useful for skewed distributions because for skewed distributions, we rely more on the median than the mean because the mean is greatly affected by outliers and skewness. When you construct your box plot, you put down your 5 numbers on a number line. So you put down your minimum, you put down your quartile 1 or lower quartile, you put down your median, your quartile 3 or upper quartile, and then the maximum. So there's my 5 numbers. We draw a box around the lower quartile and the upper quartile because that's the middle 50% of my data set. We put a line where the median is located. And then this is the whisker part. You might have heard of box and whisker plots. We connect the minimum to the lower quartile, and we connect the maximum to the upper quartile. And that is how you construct a box plot. In doing so, you have chunked your data set into quartiles, like I said, and there's 25% in each. So 25% of the data is between the minimum and the lower quartile. 25% of the data fall between the lower quartile and the median. 25% fall between the median and the upper quartile, and 25% fall between the upper quartile and the maximum. If you've ever taken a standardized test, it's just kind of similar to when you've heard of percentiles. Like if you're in the 80th percentile, you'd be somewhere in this you'd be somewhere in this upper portion, just above the 75% mark, which is right at the upper quartile. So we're going to construct the box plot for the power plant data. So you take your number line, you'd scale it out, making sure that it will include your minimum and your maximum. So I went from 0 to 110. The minimum is at 6, so this is at 5. 6 will be right here. Quartile 1 is at 10. Quartile 2, or the median, is at 18. Quartile 3, upper quartile, is at 31, right about there. And the maximum is at 104, which would be right here. I draw a box around quartile 1 and quartile 3. I draw in my median line. I connect these with my whiskers. And then it's always wise to also just state what the values are, because sometimes if you have the original chart, you don't really know, is that 5 or 6? So I'm going to put 6, 10, 18, 31, and 104. Helpful to be as descriptive as possible when making your box plot. And you'll notice here, the first thing is, what do you notice about the 104 data point? I mean, it looks to be very far away from the majority of the data, and we would say potentially it might be an outlier. So it appears to be an outlier, far away from the typical value. And before, we didn't have a measurement to determine what is an outlier and what is not an outlier. Well, that's going to be different today because I can actually define what an outlier is. There's a specific rule for it. And in order to determine what an outlier is, you first need to know something about what's called the interquartile range. The interquartile range is nothing more than how wide was this box that I drew. It's the difference between quartile 1 and quartile 3. So the interquartile range is the difference between the third and the first quartiles. It's how wide was that middle 50% box that I drew. Where are the middle 50%? How far apart are they? So the interquartile range is quartile 3 minus quartile 1. For our nuclear data, like I said, that'd be 31 minus 10. So interquartile range, 31 minus 10. It'd be 21. Using the interquartile range, I can now define the rule that statisticians use for determining an outlier. So an outlier is any data point that is more than 1.5 interquartile ranges below quartile 1 or more than 1.5 interquartile ranges above quartile 3. We call that point an outlier. Our new minimum and maximum is the lowest or highest point that is not an outlier, and we only extend our whisker to that new point. We use a dot to show any points that are outliers. So what we do is we test to see, is there any point or points that are more than 1.5 interquartile ranges below quartile 1 or above quartile 3? If they are, then they're an outlier, and we just denote them with dots. When we draw out our whiskers of our graph, we only go to the furthest point to the right and to the left that is not an outlier. Any points that are outliers are just denoted with a dot. So what we're going to do is determine if that 104 is an outlier, or maybe even if there's one on the lower end. So the first thing we need to do is find what is 1.5 interquartile ranges. So 1.5 times our interquartile range. Our interquartile range was 21, so we need 1.5 times 21. 1.5 times 21 is going to leave us at 31.5. So if I am more than 31.5 above quartile 3 or below quartile 1, I'm going to be an outlier. Well, let's find what those values are. So quartile 1 minus 1.5 IQRs, that would be below quartile 1. Well, quartile 1, if we go back and see, was at 10. So 10 minus 1.5, whoa, sorry, I want to actually input what that was. 10 minus, we found 1.5 interquartile ranges was 31.5, and that's going to turn out to be negative 21.5. And this happens a lot with the lower bound, is because we're using real data, you can't go negative nuclear power plants, so there isn't going to be a lower outlier. So not going to happen. For the 1.5 above quartile 3, so quartile 3 plus 1.5 IQR. Quartile 3 was at 31. Then plus 31.5, that is 62.5. If I am more, if the number is bigger than 62.5, it's going to be an outlier. So I go back and look at the original data set. The only value bigger than that is the 104. So the 104 is going to be an outlier. And when I construct it, then my new box and whisker plot is going to look like the following. There are no values that are obviously below this, so there are no lower outliers, and there is one value that is above 62.5, so that is why 104 is an outlier. And I denote it with a dot. My new maximum then is 59 when I draw my box and whisker plot, and that is the rule that we use for determining an outlier. Once I have a box and whisker plot, I know how to draw them and graph them. We can use them to answer questions. So here's an example that's already been constructed for us. So refer to the data shown below concerning the hourly earnings, so hourly rate for railroad equipment manufacturers. Be aware when I construct a box and whisker plot, it makes it into quartiles. So that means 25% are in here, 25% here, 25% here, and 25% here. So the first question says 75% of the manufacturers made more than what per hour? Well, that would be the upper 75%. So these three combined, well, that's $15.12.5. So $15.12.5 per hour made more than 75%. We would call that the upper 75%. 75% of the manufacturers made less than what per hour? Well, that'd be the lower 75%, these ones, and that's going to be lower than $17.65. And then the last one says you randomly select a manufacturer. What is the likelihood they made more than $15.80? So that would mean they were somewhere in that range. Well, that is in between the median and quartile 3, and quartile 3 all the way to the maximum. That's the upper 50%. So 50% is the likelihood that they made more than $15.80 because that's above the median. And that's the usefulness of box and whisker plot once you've constructed it, is you can quickly answer questions like that and get a sense of what percent made above this, below that, and just a general idea of the data set. Going to give you one chance to try what we've been talking about, and it says the following: the prices of 10 houses in Helena are shown below. We already did this with a 5-number summary, so you have the 5-number summary from before. Make a box and whisker plot and then answer the following questions. You should also check to see if there are outliers. So question 1, 50% of houses cost less than what? What is the likelihood a house in this neighborhood will cost more than $300,000? So pause the video now, give yourself a chance to try before coming back and seeing what the answers are. Okay, first one, so remember, so here's your 5-number summary. When you make the box and whisker plot, you see the following. You see that 700 turns out to be an outlier, 350 is your new maximum. Your interquartile range was 120, and 1.5 times 120 is going to be 180. So if you are more than 180 above quartile 3, which would be 480, so if you're more than 480, you're going to be an outlier, which is why 700 was an outlier. 180 minus 180 is a 0, so if you're below $0, you'll definitely be an outlier as well, but there's no house that's $0, so there's no lower outliers. And then we can answer some of the basic questions. It said 50% of houses cost less than what? Well, cost less than the median, so cost less than $240,000. And then what is the likelihood a house in this neighborhood will cost more than $300,000? Well, that would be in this range, and that's the upper 25%. So there's a 25% likelihood that you're going to cost more than $300,000. That is it. Thank you very much, and have a good day.